In last class we had started, or rather we had finished work with the multiplicative cipher, and that came into existence with the form that additive cipher we already knew. To be honest, the Caesar cipher that we have discussed, that is in a way coined as additive cipher, because primarily we are doing addition, so that's why it is called also as additive cipher. And the multiplicative cipher was primarily where the keys will be present in the same manner, except that a multiplication operator will act. And in that aspect, we have discussed a very important mathematical tool, and that was given by multiplicative inverse, which will be helpful in near future also, as I said, during the second module. But I had introduced you the concept of how to calculate the multiplicative inverse, keeping in mind that the algorithm that we are going to discuss today, one of the algorithms that we are going to discuss today, will also require the multiplicative inverse, right? Which is nothing but in that new algorithm, which will be a combination of both the additive as well as multiplicative inverse. So if you remember, this is where we ended our discussion with, where we had deciphered correctly, or rather encrypted and decrypted correctly the word, the plain text, and using the multiplicative inverse process, we found out with the that what should be the k inverse for that matter, and based on that we had found out something like this, okay, something of this nature, and we found out the answers for the same. Now based on that, this is where we stand as of now. Okay, the additive cipher is the one, the first where we started off. The second one is the multiplicative inverse, multiplicative cipher that we have discussed. Now if we combine both these two and you form a third one of its kind, this is where we call that as an affine cipher. We'll come to that in the next slide. Don't worry, this is just a diagram to represent that how they are combined. So the first diagram is indicative to the additive cipher. Remember this word additive cipher. So like up till this point I might have missed the term additive cipher. The first term is basically the first Caesar cipher that we have discussed. Same thing. It's just a synonym for that. So the first one is the additive cipher. The second one that we are looking at over here is the multiplicative cipher, which we discussed in this class. And finally, we come to a affine cipher, which is basically a combination of both. So to understand that, let me just show you the second diagram, which might be easy for you to understand. So if you observe the diagram carefully, there are two keys that we are using, and they are called as pair of keys. So in the pair of keys, you can see the K1 and K2. If you take the left hand side, it's basically K1 and K2. So this K1 and K2 holds as a pair of keys. Now it can be like 7, 2, 11, 4, whatever it is. There is no specific combination to it. Any two pairs can be possible. But what happens is that you can see that intermediate, there are two ways, two in between steps are happening. One, that is a temporary key. You can see that one in the left hand side, capital T is equal to P multiplied by K1 mod of 26. And the output of that is fed to the second one, C equals to P plus K2 multiplied by mod 26. So basically these two steps uses two separate keys. One in K1 and the other one is K2. This is the most important portion of this affine cipher which you need to keep on knowing. Until this point we have discussed only about single key encryption. But this is the first time we are introducing two keys or a pair of keys, and if you replace K1 by K2 or K2 by K1, the meaning is completely different. So please make sure that that's a note for all of you. And instead of this two, the easiest solution is, you can see the first, the generic equation that we have mentioned over here as C equals to P multiplied by K1 plus K2. So please make a note of that. That's the encryption formula for affine cipher. So the generic formula, you don't need to worry about these two steps actually. So the generic formula for an affine cipher is C equals to, that is the ciphertext is equal to P, which is the plain text once again, multiplied by K1. Remember this order. K1 is multiplied by plain text plus K. And then you have mod 26. Right? So this orientation of K1 and K2 is very, very important. If you misplace any one of them by K1 to K2 or K2 to K1, the meaning is completely different and the algorithm doesn't go. And on the other hand, if you observe the description, that's also very similar to that of the previous two. And it is also the combination of both these two. You can see on the right hand side, both of them are going together. Same way, capital P is equal to P multiplied by K1 inverse. And the second step, if you observe, capital T is equal to C Actually, the step is over here. P is over here. This is the first step at the decryption, and then it goes up. You can see the arrow. Okay, the P is basically the plain text that we are retrieving. So up to this point, if you see the C is comes over here, the C comes over here through this channel, and it is paid over here. So capital T is again being called upon, which is given by C minus K2 multiplied by mod 26. On the other hand, we have that T is being used in the first step or the last step in the decryption, and it is given by T multiplied by K1 inverse. Now, if you observe again, the generic step is given over here on the right hand side. Please make a note of it. C minus K2 multiplied by K1 inverse. See the difference. Here K1, K2 is the arrangement in the encryption. In the decryption, K2, K1 is the arrangement, and K1 only has a multiplicative inverse. K2 doesn't have anything to do with it. Only K1 you require to have an multiplicative inverse. Hopefully now you are already aware of multiplicative inverse, how it is to be done. Okay, so I'm neglecting that part. So C minus K2 multiplied by K1. So if this is what the idea is, can anyone please do the process of encrypting this particular message using the affine cipher? This is the encryption I'm talking about, where the key here is 7, 2. So the arrangement is K1 minus K1, K2. So basically 7 stands for K1 and 2 stands for K2. So please make a note of this and try to solve it. So we have the pair over here 7, 2. So what I am mentioning is that this 7 indicates K1 and this 2 indicates K2. So these are the two pair of keys 7, 2, and I want you to do first the easier one, which is the encryption. First do the encryption for me. The encryption, the cipher text, in fact it's mentioned over there, so you can very easily you can verify the answer whether it is correct or not. But naturally in your exam it won't be provided to you. So in this case as an example you can do it. So basically what you have to do, you have to perform the process. Yeah. So in this case you have to use a process where you have C, or if I say C1 as P1 multiplied by K1 plus K2 mod 26. Here C1 stands for the first letter. So that's H that you are replacing with. So in that calculation part you can do it. 7 multiplied by 7 plus what is K2? We have 2 as K2 mod of 26. So it's 49 plus 251 mod of 26. Am I okay with this? So let me just. So anyone any doubt with this? Encryption is relatively easier, but the only thing is the alignment of K1 and K2. That's the only problem. So let me just, if anyone is ready with the answer. Anyone ready with the answers? Please check it for yourself. Whatever the steps you have done, up to what stage you have done, this is basically the final answer that we are getting. So your cipher text will have 25, 4, 1, 1, 2, 22. So in the same process, you go back to the table once again and you check that 25 belongs to which letter, 2 belongs to which letter, and so on and so forth. And you can find out that what is the cipher text for it. It's the same process except that the orientation is that we are doing an addition as well as a multiplication in some. and there are two keys which we are taking care of in order to solve it. Right? Can anyone quickly give me the multiplicative inverse for the decryption process? Multiplicative inverse of 7. That's why I took this example, because we had already done it in last day's class and we had calculated 7 and the multiplicative inverse of 7 was 15. So you can directly substitute in the right hand side equation and you can find out whether the decryption process is also correct or not. You can verify at least for one if you can do it just for a practice. So please try to do the decryption also. So you suppose you take C as 25, 25 minus 2 multiplied by 15 mod of 26. I am avoiding the steps here because it's a repeated process itself. So this will be for the first letter. So it will be 23 minus multiplied by 15 and whatever the product you are getting, divide that by 26. Consider only the remainder as the process includes. Okay. But remember, to find out this multiplicative inverse, that's a separate calculation that you have to perform. Here it's easy that we have found out 7. We have taken 7 and in the previous example we had taken 7. So we can easily assume that the multiplicative inverse is 15. But in exam, when you are trying to do it, you cannot write that, right? So you have to do either the process of trial and error method or you have to find out using the GCD method to find out whether what is the actual value of multiplicative inverse. Correct? This is fine for all. In that context, let me give you an example. Let's see whether you are able to find it or not. Just write it down. I will just try to note down over here the example. Okay, so please make a note. The plain text suppose is given as Monday. Plain text is Monday and the K1, K2 key, that is a pair of key, is given by 11, 4. The question is to encrypt the data and naturally it will decrypt it as well. Please try take 2 minutes of time to let's see whether without looking at anything you can solve it or not. As I said, please try to practice because this is the type of question that will be there. So as much as possible practice it and there is no end to this practice. You can take any number of data, the process will be the same. So in material how many times I solve, but it's about how many times you practice. Alright, so please take a note of it. You have the equation, you have the database. I would say it's rather advisable to write 0 to 25 and A, B, C, D on top of the answers always. Because now, for example, I don't have the table with me, but at least to keep it in mind, you just keep a note of like this: A as 0, B as 1, C as 2, like that, so on and so forth. Z as 25. So this is you might keep it with you so that you don't have any problems. Please try to solve it and give me the answers correctly. I'll give you 4 minutes. So I'm ready with the encryption part, cipher text. I will give the final answer. You check that whether you have done it correctly. The cipher text should look like GCRLEI. Anyone having problem with the encryption part? K1, K2, multiplication, anything? Right? So this is the encryption part. I want you to also do the decryption as well because there is the need of multiplicative inverse. I want you to find that. For the time being, for the lack of time, whatever we have, you can try the hidden trial method also to find the multiplicative inverse. Otherwise, you can also try the process that I told you in last class. No problem at all. Last class, the process was more accurate, to be honest. You will save much less time on that. So you can use it. For which you need to find out the multiplicative inverse. And if you have closely followed my class, have you not done a multiplicative inverse of 11? What was that? So basically, we have with the same intention I did that in previous class so that our time gets resolved. So the 19 was basically we have discussed the complete steps of how to find the multiplicative inverse, keeping 11 in mind. Yeah, this I don't think I'll go back, then it will go out. So basically your K1 inverse is nothing but 19. So keep that in mind and decrypt and get the final result. Once again you are supposed to get back Monday. That's the but the only point is that calculation of K1 inverse is what the T is. Okay, and process of which one you choose as K1, which one you choose as K2, that is very important. Don't mix and match. It will be erroneous. Should I wait for the process or like okay for all? Any doubt with the affine ciphering? Any problem? Okay, fine. Alright. So this is I was talking about. I was talking about this one in fact. In previous class we had already solved how to find out 11 and its multiplicative inverse. So that's what we came as 19. So that same thing is being used over here. Just a different example. So let us now discuss another very interesting ciphering process, and that is called as monoalphabetic ciphers. Okay, and we'll soon find that monoalphabetic will give rise to polyalphabetic cipher as well. Okay, so this is a little bit different to that of the Caesar cipher, be it the additive or the multiplicative. In the process is that why? Because in case of Caesar cipher, one of the biggest drawback of the process itself was that we were mapping each and every time one letter A, suppose with 0 and Z with 25. So there was a specific arrangement of the cipher text which will always happen. That's why the brute force attack was so easy on a Caesar cipher process, that we understand that after a certain period of time the key will be available open. That's what we did. So what the monoalphabetic ciphering means is that here instead of one-to-one mapping there will be one-to-many mapping. By that what I mean is, if you observe the example given over here, the table that is given over there, plain text you have A to Z, right? And the green colored cipher text that you are looking at, over here, this is one of the sample combination of each and every plain text to ciphertext. Meaning that this combination, for example, A is combined to N, B is combined to O, C is combined to A. If you see, there is no pattern to it. The only condition is, if you see the last line mentioned over there, a single unique cipher alphabet is used per message. What does that mean? Suppose I have a letter, I would say, my name is Mohan. I'll give you this example so that you will be able to understand. My name is Mohan. Suppose this is my sentence for plain text. If you are looking at Caesar cipher, what will be the process? For M, you will be marked with what is the M is mounted to this number? 12, whatever it is. So you will be using that for here, you will be using it over here, and you will be using it over here all the time for the Caesar cipher. But for polyalphabetic cipher, what they indicate is that if you are using N over here as A, suppose, for this second alteration it might be B, and for this third appearance it might be Z. Understood? So there is only one to many. A single M is mapped to A, B and Z. This is the possible way of doing it. There should not be any repetition of the ciphertext or the keys for that matter per letter. So that is why it is very much important, because if you observe there, as I think it's mentioned, 4 into 10 to the power 26 possible keys are possible if you are doing this. If you remember in case of Caesar cipher, how it is different. In Caesar cipher there was only 26 keys at max, and that's why the cryptology shows that whenever we have a brute analysis, it was very easy to do it. Right? We were able to find the key very easily. But in case of monoalphabetic cipher, and even in leading to polyalphabetic also, the number of combination goes beyond to 4 into 10 to the power 26 possible keys. It is a pretty huge number of keys, possible keys. And naturally, brute force attack is which we are supposed to avoid. Even if you do it on it, you won't be able to properly get back the key back. You might be lucky, that's a different issue. But if you are not, your process is in that way that you are searching for each and every time. It's not possible to use 4 into 10 to the power 26 number of keys to find out or decipher a date. That's the logic. Right? So if the arrangement that you are looking at, this is not the only arrangement. It can be many other as well. It's not that A will always be mapped to N or B is mapped to O. It can be different. The logic is this arrangement that you are looking at, the mapping that you are looking at, should be there with the transmitter and should be there to be known to the receiver. This table. Suppose you and your friend, you are talking amongst yourself using a monoalphabetic cipher. You should tell your friend that this is the combination of the mapping that I am referring. You should also decipher based on that. Simple as that. Rest of the process is absolutely the same as that of previous one. Same. Whatever the data you have, the text you have, you repeat it accordingly, change it with the alteration, and you get the result. So that's basically monoalphabetic cipher. So first things, one of the very important thing is we are trying to make sure that the brute force attack can be prevented using this process. But there is something else that we cannot avoid, and that's why that is the drawback of this process. And that is where the cryptanalysis, as I said, for the serial cipher we have also done that. And that is called as the frequency of appearance of the letter. In light of that, even if you are using this many number of keys, it is not that very secure. And how is that? We will see that in the next example. So suppose this is basically, this is just an example based on the table that is given over there. So suppose the plain text is this message is easy to encrypt but hard to find the key. Okay, so this is basically the plain text, and if you go by the previous example, okay, so in that way we are getting that huge letter. If you observe over here, this one is the encrypted key. There is nothing new to it. This we already know. Only the point is this particular arrangement that we are talking about over here. This is unique to a combination. Based on that, we are doing it. So there is no such very important thing over here. The important thing is over here. Just now look at it very closely. Now if you observe the good 3 lines of ciphertext that we have mentioned, using suppose some kind of a combination that we have, even if you don't know the table tabulation, we are actually have an option of deciphering it, that what the message is without even looking at the key. And that is where this frequency analysis comes very handy. To understand that, let me just start with something and then I'll discuss a bit more. The process is, you can see the left hand side, this table, if you observe carefully, this table, the left hand side table that you are looking at, this is the frequency of letters and the occurrence of the letters based on the message that we have. Based on the message that we have. So you can see P is having around 13.33. I think this already you are aware of what does the 13.33 mean. We have discussed in last day's class. So that is basically the sample table based on the 3 lines that you are looking at over here. How many times P has repeated, how many times Z has repeated. So naturally you can see from the outset itself, it's quite obvious that P and Z has appeared multiple times. So P and Z is lying around 13.33 times and 11.67 approximately. And the right hand side table, this one that you are looking at, this is the old table that I have discussed in last day's class. That's a standard table of occurring the number of letters in English alphabet. Same thing. What we are supposed to do is, for the start, we will start finding that which letter in the present ciphertext is having the maximum frequency. Which letter is having the maximum? P. P is having around 13.33, which can be mapped very closely to E for a start. And we can also say that for all the Z's which we have over here, we can map it to P. So first thing is that we are assuming that for single letter, P can be assumed to be about equivalent to E. So wherever you have P over here, you can replace. So for example, here we have a P. So you can replace this by E wherever the P appears, and wherever the Z appears, you can replace this by E. Just for the start. And you can go on doing it. But the problem starts in, unlike in the previous day's example, that after a certain period of time, you can observe that in the left hand side table, the one that is the current table, it has some elements which are having similar kind of probability compared to the previous example. 8.33, I think you will observe S and U is having 8.33, which is equal occurrence. So in those cases, single digit comparison might not be a very profitable option. It might even give you the skeleton of it, but it will take more time to do it because you are assuming in a way that it might happen, this later might happen, or the other might happen, so like that. Instead of that, the process is that we will try to find out a die bit, or we call it a die. We will use the word. Maybe I'll just let me do one thing. I'll just open, because I have to cross both times, so I'll just reopen this one once again. Please make a note of this. The logic is that instead of one letter, we are going to use two. We are going to find two letters. So instead of one letter, find diagram. This is the word I wanted to find. Diagram, which means it's a combination of two letters. Which means that after, if you have a doubt with the single letters and its frequency, we will try to find in the all three letters or the three sentences that we have, do we have a scenario where two letters combined that has repeated multiple times or not? If you go back over here, and if you check ZW, I think I have marked it as red. ZW, if you observe this word ZW, it's a two-letter word, a diagram we are calling it. So ZW has appeared multiple times, right? Usually in English, whenever we have this two letter and the maximum of the frequency of two letters that might appear multiple times is given by PH. So please make a note of that. So this diagram we call it. This TH is a standard. This is from a standard. So TH is the maximum appearing two-letter word in English vocabulary. So what we are going to do in this case, ZW is mapped to TH. I'll repeat once again what I'm trying to do. As the single letter detection might not be correct, because in some cases we are observing that the probabilities are almost the same. So what we have to do is we have to club two letters and we have to find out whether those two letter combination has repeated multiple times or not. And if we find any one of those two letters, we will map to TH, because TH is as per standard the maximum used diagrams in English language. So ZW is mapped to TH, right? So if this is the case, already in the first step, what you have assumed Z to be as? Here, Z was 11.67 at the very first step when we were taking single digit. Z was mapped to T. Was it not? Z was mapped to T, right? So, if you go back here, so you have already assumed this as T. So definitely your W is mapped to H. So basically what I mean is, wherever you will get T, you are replacing that by E. So whatever we have observed so far, T can be replaced by E, Z can be replaced by T, and W can be replaced by H. So we at least got three of the notation of it. Same way, we go on finding three digits which are being repeating multiple times in the same example or in general. And the 3-letter, or we call it as a trigram, is the maximum use is the. THE is the maximum frequency of usage in English alphabet. And in this particular example, you find that ZWP will appear as a 3-letter word which has appeared maximum time in the text. Can I repeat it once again? Any doubt with this? First we started with single digit. We have mapped P and Z to E and T. That's done. Because based on that we are finding out that for single digit the comparison is almost the same. So we cannot do anything. So now we are trying 2-letter word which have a combination and has repeated multiple times. That we are mapping with TH because TH happens to be the maximum used 2-letter digit word in English vocabulary. So in that way, ZW has been mapped to TH because ZW happens to be the 2-letter word we use maximum time. And since in Z we have already assumed that as to be T, so the leftover that is W will always be H. Now, with the 2 letters done, if we don't find anything as 2 letters, we will go to 3-letter word. And then the 3-letter word we are finding out, you can see it later on with the message itself, that ZWP is a word which has repeated multiple times. And thus, we are replacing ZWP or we are assuming that to map to ZH. Now, if you observe carefully, Z has already been mapped to T, W has already been mapped to H, and T rightly has been pointed out as T. So we are getting a confirmation of the same, that the assumption that we have made is actually right. In the same manner, if you go on with the 4-letter word, you will find the 4-letter to be ZWSZ. This also will be a 4-letter word again, which has repeated multiple times, and this will be represented by PHAT. This that is again the 4-letter English word which is being used maximum time in the English alphabet or using the English vocabulary. Understood? The process is simple. We are trying to find out the frequencies. So starting with single letter, then 2 letters, then 3 letters, then 4 letters. And if you observe now, if that is what the keyword is, Z is mapped to T, W is mapped to H, Z is again mapped to T. So we are almost getting very similar answers. So naturally we can assume that S will definitely be mapped to S. So we are getting another set of element where S can be mapped to A. Is it understandable to all? Should I repeat it once? This is the crux of monoalphabetic ciphering, as rather the cryptanalysis of monoalphabetic ciphering. Brute force attack we can avoid a bit because we have so many number of keys possible. But if you observe here carefully, that we are even without the key, just by observing the pattern in which the letters have appeared, we actually can find out what the letter is or what the message is. And if you observe, if I go back to the presentation once again, you can see the bottom half of the nature of it, and you can see some of the words that is mentioned over here. This is the word ZWSZ. We have just now mentioned it. Similarly, you can see PATEA, that. So some of them are already, the skeleton of it is already available. And if you go on doing it, in the same manner, you can see the right-hand message itself. The final message, it was disclosed yesterday that several informal but direct contacts have been made with political representatives of the DH Congress in Mumbai. So this is the old message. But if in the same process we go on repeating it, we try to find out the 5-letter word which has the maximum, or 4-letter if suppose it has repeated multiple times. In that way, some guessing game. The more you get the data, you just replace that in the original list, and you try to find out what are the elements. So that is basically the cryptanalysis of a monoalphabetic cipher and the problem with associated digits. So the monoalphabetic cipher, the advantage is that we are mapping one is to many. But the problem here is that in terms of the frequency analysis of English literature or the process, we can decipher them quite. In fact, this leads to the second application of it or the modification of it, and that's where we discuss about the polyalphabetic cipher. But I don't know whether we have time or not. Just I'll give you the briefing of it. Maybe we'll take the example on Wednesday's class. Over here, what we do is, in the same manner we do it, but here we will use a table. We'll use some kind of a table in order to make things a little difficult for the cryptanalysis to happen. Okay, so this is basically the process. The general name for this approach is polyalphabetic substitution. All these techniques have the following features in common. There are 2-3 methods of it. We'll see that one by one. A set of related monoalphabetic substitution rules are used. A key determines, see the which is little bigger in size. A key determines which particular rule is chosen for a given term. So along with the monoalphabetic, the way 1-to mapping is happening, along with that we will set some rules in selecting the particular key from a given set of pattern of keys. That will make things even more difficult for cryptanalysis. So let us stop at this point because there are 2-3 methods. Instead of dividing that into 2 halves, let's finish up on that note. When we come back on Wednesday's class, we are going to start with the polyalphabetic ciphers and its. Thank you.